So first, let me show you how to load the simulation pack module into Mathematica when you're unfortunate enough to be running it under IU Anywhere, which I know is not the greatest system in the world. So you type capital G get, oops, what's going on? Let me try that again. Capital G get bracket quote, and then just start typing anything, I think, but starts typing simulation pack, but then a button should open for the file browser, and it's a lot easier to find the file that you need using the file browser rather than trying to type in the whole path in text. So now what you presumably what you should have done is you should have saved the simulation pack file, it's a .m file, to either your Dropbox or your Google Drive or your OneDrive, that is that cloud storage server that you'd given IU access to. So that would mean it would now show up when you log into IU Anywhere. So for example, if this works, yeah, there it is. When you open this PC, you'll see my Google Drive is available at the bottom. So that's my personal Google Drive, so I'll click on that. And then I'll open my 447 folder and my sim folder. And then I want the simulation pack. I actually want the M file. That's the one you want to load this way. Okay, so now it typed in the full path, the simulation pack. I now want, I'll just close the quotation and close the bracket, and then I can enter that into Mathematica, and then I'm good to go. So having loaded the simulation pack into Mathematica, now we can actually perform a simulation. So let's start with the very simplest one that we talked about the other day, rolling a die and just checking, trying to determine experimentally through the simulation, on average, how many times do you have to roll a die in order to get a 6? So we decided that to simulate that, we would have states that have two attributes. R would be the value of the current roll, a number 1 through 6, a whole number 1 through 6, and T would be the number of times a die has been rolled, also a whole number, but it could be anything from 0 on. Okay, and then the update algorithms we came up with, we said every time we want to update the roll, we have to choose a random number from 1 through 6, and to update the time, we simply increase the old time by 1. Okay, so that'll be, it's pretty simple, right? So we can concentrate on how you do this stuff in Mathematica without getting bogged down on the mathematical details. So in Mathematica, we're going to represent states by what are called association lists. Now this is, actually it goes by different names in different computer languages. So sometimes it's called dictionaries, sometimes they're called maps, sometimes they're called hashes. But they're all pretty much the same thing. It's basically an association between keywords and values, right? You can also think of it as a function, right? So the keywords are like the inputs and the values are like the outputs. It's like a dictionary in the sense that you give it a keyword, you look it up in this association list or dictionary, and then it tells you the value, right? So the notation or this format in Mathematica is that an association list is surrounded on the left by angle bracket vertical bar, and then on the right by vertical bar angle bracket. But right, the left angle bracket on the left, right angle bracket on the right. Okay, so that's just how they do it in Mathematica. And then in the middle, we will put in the keyword and value pairs. Now, for this system, we're simulating a die roll. We only need 2 entries in this dictionary or association list. We need to say what the roll is, so I'll call that R. So I'm just going to type R. That'll be like the key or the keyword for the roll. And then what you do is you type in an arrow, which you do by putting a minus sign and then an angle bracket, or like a pointing right. And then I'll enter 0. How about that? Notice that after you've entered the thing after the arrow, Mathematica automatically turns the arrow into a nicer looking arrow. So instead of being just a hodgepodge of two different symbols, a minus sign and an angle bracket, it looks like a real arrow now, right? So that's kind of nice. That means you entered it correctly. I'm going to enter the initial roll, or the roll for the kind of the model state here that I'm constructing as 0. That's not something you can actually roll when you roll a die, but that's okay because the state I'm entering now is kind of going to be the initial state of the system before we've actually rolled any dice. So it kind of makes sense that the die roll would have a nonsense value initially, right, before we've actually rolled the die. Okay, so that's one entry, right? So this says that in this state, which as I said, this is going to be the starting state of the system before we've actually rolled any dice, the R value is 0, and I should also give it the T value. Well, that will also be 0, so I'll enter that the same way. Okay, so the R value is 0 and the T value is 0. Now you can enter that into Mathematica, right, and it records that the state is that value. Now, let's just, oh, I'm sorry, now I have to enter the updater, right? So the updater is this basically a list of algorithms or functions that you use to update the values in the, or the attributes in the state. Okay, so there's going to be one updater for each of the attributes in the state. So now let me immediately point out that the format for the updater is different. The updater is not an association list. The updater is actually just an ordinary list, so we just use curly braces for the updater. Maybe before I forget, I'll also put the right curly brace at the end. Okay, so there's my updater. It's going to be a list. And each item in the list is actually a rule. And a rule, in this context, is a colon followed by a right angle bracket, which is a kind of a colon arrow. Okay, let me do time first because that one's simpler. The new time is just going to be equal to the, let's see, so I just type T, and that's going to represent the new time. Then I'm going to type colon right angle bracket, or greater than sign, and I want to say that's going to be equal to T plus 0. Oh, T plus 1, right? So that's the rule for updating the time. Now you have to understand here that we've got this symbol for the rule that's applied to produce the new value from the old value. So it's taken for granted here that the T on the left is going to be the new value of T, and the T on the right is going to be the old value of T. So I don't have to use that notation I used in the kind of mathematical notation I used, the shorthand notation, when I said that the new T value is T sub n and the old T value is T sub O. You can't really do subscripts very easily in Mathematica anyway, so that's just as well. But this does require you to remember the convention that if you that when you refer to T on the left of the rule sign, the one on the left is the old value, and the one on the the new value. The one on the left is the new value, and the one on the right is the old value. Okay. Now let me do the updater for R. So the new value of R is going to be given by, and I want to pick a random integer from 1 to 6. Well, okay, there's a nice built-in function in Mathematica called, in fact, random integer. And all you have to do is give it, as input, you give it the range of values. So this is a list of the minimum value and the maximum value that the integer can take. Right, so this says just take a random integer from 1 to 6. Okay, and that's my updater, so I'll just go ahead and enter that. So it's a list of rules used for updating the state. Okay, now I can test this out. Just to test it out, make sure everything is working okay, I'll try to apply the updater rule to the initial state and see if I get something reasonable, right? To do this, I'll use the run command. I can run, and it takes 3 inputs. The first input is the state you want to start from, so I'll just start from the state I defined before, which is actually going to be my starting state. And then the second entry is the updater that you want to use. And then the third entry is how many times you want to run it. Well, I'm going to be modest here. I'm only going to run it once, make sure it seems to be working before I try running it like a million times. Okay, so what do we expect this to give us? It's going to take this initial state where the roll is 0 and time is 0, and it's going to update it once. So that should produce the first roll, where r now is some number from 1 to 6, and where t equals 1. In fact, this will produce a list of all the states from the first one to the last one. Okay, so it's actually going to output a list of 2 states, you know, the first state and the last state. Let's see, enter this into Mathematica. Yep, here's the first state. The first state was when, right, it's exactly the same as the initial state. The last state here, after it ran the updater once, time advanced to 1, and apparently the roll was 4 because the r value in this state is 4. So the die, this is simulating a die roll of 4. Okay, it looks like it's working right. Let's test it a little harder. Let's run it 5 times, shall we? So I'll apply the updater 5 times. So now I'm going to get a list of 6 states. I'll have the initial state, and then I'll have the 5 updates from the initial state, where each time the updater is applied to the previous state. Okay, so here we have the initial state where time is 0, then time is 1. This is the first application of the updater. The roll was 3. At time 2, the roll was 2. At time 3, the roll was 2 again. That can happen. At time 4, the roll was 6. At time 5, the roll was 4. Okay, so this seems to be working correctly. The next thing to do is we would like to gather a lot of data. So the way to do this, oh no, actually let me pause for a second. One thing we'd like to do first is we want to tell the system when to stop. So there's another command you can use for that. Oh, by the way, it'll show you the options here. So one of them is run till. That's the one I'm going to use here, run till. So now the first 2 inputs are the same. We give it the starting state and the updater. But now the third entry is not a number. The third entry is a condition for when the system should stop, when it should stop updating. Now remember, in our problem we were trying to figure out how many times we had to throw the die until we got a 6. So the condition for stopping is when r equals 6. Notice I typed 2 equal signs here because this is a test. I'm testing whether or not r is equal to 6. I am not setting the variable r equal to 6. Right? There's a difference between setting a variable equal to something and testing whether or not it's equal to something. And that's the version I want to use here, the test. So it's a double equal sign. So what this will do, it'll run the system from the starting state, right? From the starting state we have at the top. Apply the updater repeatedly until the condition is satisfied. Okay? And, you know, depending on how the random rolls of the die fall out, this could take any number of time steps. Let's see. Okay, so this time it only took 3 time steps. On the first 2 rolls we got 1s, and on the third roll we got a 6, and that's where it stopped. And notice that it just returns, the actual output value of this function is simply the last state that was reached. So the output value of the run till function is simply the last state when t was 3 and r was 6. These earlier states are just printed out to be helpful in debugging, right? Sometimes if you see you've made a mistake in the debugging, this can help you try to trace the problem, right? But the output is really just this. Okay. So, and by the way, I can run the exact same line of Mathematica again. It'll give me a different output. So that time it only took 2 rolls, right? I got a 1 on the first roll, 6 on the second roll. I can do it again. Ooh, that time I got 6 immediately on the first roll. Let me do it again. That time it took 2 rolls. I'm getting lucky. Okay, this is a little more reasonable. This time it took 5 rolls to get a 6. You get the idea, right? Every time it just rolls the dice at random. And it can take a random number of times in order to get a 6. Now what we want to do is we basically want to repeat this run till command maybe like 1,000 times to collect a lot of data. And then if we do that, we'll have 1,000 copies of this last state. In each one of the last states, r will be 6, because that's where we stop, but the times will be different in all the different from all the different runs, right? Sometimes it'll be 5, sometimes it'll be 2, sometimes it'll be 13, depending on how long it took in that run to roll the 6. So the way to do that is, well, first of all, we want to save the data into a new variable. So I'm going to say data equals, and then I'm going to use another version of the run till command. I'm going to use run till many. So that'll basically apply the run till command many times. So the basic scheme is the same. First I give it the starting state, then I give it the updater, and then I give it the condition, just as before, r double equals 6. But then at the end I tell it how many times to repeat this. So let's say 1,000. I'll give it 1,000. We'll collect like 1,000 data points, right? We'll perform this experiment 1,000 times. And that'll be enough to get a good idea of what the mean value is. I'm going to put a semicolon at the end because I really don't want to look at 1,000 runs here. So the semicolon will suppress the output. So let's try it. Let's enter this. Okay, it's going. Reached 1,000. Didn't take too long, right? So it did 1,000 rolls, and it stored the results in the data variable. If you want to look at individual entries in the data variable, you can call them by using the double bracket symbol. So the first entry in data is from a run where it took 4 rolls in order to reach a 6. The second entry in data, so I'll put 2 in double brackets. The second entry, it took only 1 roll to get a 6. And what about, I don't know, the third? Or it took 2 rolls, okay. Gee, am I lucky? Okay, let's look at the 10th roll. Only took 4 rolls. Okay, oh, the 10th run took 4 rolls. Okay. So that's what the data looks like. It's just a list of states like this that represent the final states in a run of this simulation where we kept rolling the die until we got 6. Okay, now what we really want to do is we want to get the mean of all the times, right? Okay, so fortunately I provided you with a handy-dandy utility for calculating the mean of one of the attributes from a whole list of states, right? So this data variable is actually a list of 1,000 states, and I'd like to take the mean of the t attribute in all of those 1,000 states. Okay, so I use the mean of command, mean and then capital O of, and it takes 2 inputs. First you tell it what list of data you want to use, so I'm just going to use the data called data, and then you give it the expression that you want the mean of. So I want the mean of r, right? The attribute r. No, I'm saying not r, t, right? I want the mean of the time. I think we know what the mean of r would be, right? So, oh, that's not too bad. The mean time it took was 6.247. So it takes a little longer than 6. Now, I've kept you in suspense, but you know the theoretical value here, the average time it takes to roll a 6 is in fact 6 rolls, right? Because a standard 6-sided die has 6 possible outcomes. They're all equally likely, so on average 6 will come up on 1 out of every 6 die rolls, and that means on average you have to wait 6 die rolls until the 6 comes up. Okay, so the theoretical value is 6. The experimental value that we got from this simulation was 6.247. It's pretty close, but you know, you could probably do a better job if I ran it like, I don't know, like 2,000 times. Why don't I do that? Let's see. Why don't I change this to 2,000? Oops, 2,000. Okay, 2,000 runs, and then I'll take the data, I'll take the mean of t again. Ah, that was not really any better, but it was on the low side. So you see how variable it is, right? Let's try. Now I'm hooked. I got to try it until I get a more accurate version. Let's run it 10,000 times. This will take a few seconds. Rolling the dice frantically. Okay, there we go. 10,000 rolls. What's the mean this time? Ah, that's pretty close, right? That's pretty close to 6. 6.03, accurate to, you know, like. Well, 1 decimal place anyway, right? So, so that is incidentally something you might want to do. See how much variation you get on different with different data, right? And see if you want to increase the number of runs in order to get a more reliable mean, right? Oh, which is something you want to do. By the way, one other thing you can do is you can take the standard deviation. Now, what was it? Standard deviation. Oh, I don't remember. Oh, maybe it was the variance. Variance. That's right. I didn't call it. So I didn't give you a standard deviation, but I gave you a variance. So the variance of t in this data. Remember, if you've had probability or statistics, the variance is the expected value of the square of the difference between a particular value and the mean, right? So that gives you a measure of how spread out the thing is. So in this case, the variance is, let's see, about 30. Remember, that's the square of the difference. It's the mean of the square of the differences. So to get an idea of how spread out the values are, you'd want to take the square root of the variance. The square root of the variance is the standard deviation. So why don't I say standard deviation, that's equal to the square root of the previous output. Remember, you can use the percent sign to just recall the previous output. So that's the standard deviation, about 5.49. That's pretty high, right? It's still pretty high. So yeah, there's still some uncertainty in the value here, although we happen to know that it is close to the theoretical value. But yeah, I mean, if you roll a die at random, then the possible variance in the number of times it takes to get a 6, it could actually be pretty high. I mean, there's no limit on how many times you might have to roll the die. You might have to roll the die 100 times. You might be extremely unlucky and roll numbers less than 6 for the first 99 rolls, or for the first 999 rolls. So there's no limit on how many times you might have to roll it. So yeah, so that's something else you probably calculated in, let me see if I remember that, in probability theory, is the variance and the standard deviation, the theoretical values for this distribution, for the geometric distribution. And let's see, looking it up, I see that the theoretical value for the variance is actually 30. Okay, so the theoretical value of the variance is actually 30 for this situation. So okay, so our empirical value for the variance, right, from the simulation is close to the value it should be also. So that's pretty encouraging, right? Okay, we can easily adapt the simulation we just constructed to do the next one that we talked about. Rolling a die until 3 6s in a row come up. All we have to do is add one attribute. We have to add this attribute L, which represents the current length of the run of 6s that we've gotten. And of course that means we also have to add one extra updater, right, to the updater list. Okay, so we can just easily modify the existing simulation we're doing. So I'll add an attribute L here, and remember, L is supposed to be the length of the current run of 6s. Initially that's going to be 0, right? So we can make the initial state to have the attribute L equal to 0, and then we have to add an updater for L. So L is updated with, let's see, now remember, when we were describing it previously, we used a piecewise defined function, right? A case-wise defined function. Ln, the new value of L is going to be 0 if the new value of R is not equal to 6. But if the new value of R is 6, that means we're continuing our run of 6s, and we want to increase the L value by 1. So a simple way to do this in Mathematica or any computer language would be to use an if statement, right? We just check if the value of R is equal to 6, then we do one thing, otherwise we do something else. Okay? So in Mathematica, what we can do is we use the if command. It works just like any other function in Mathematica. You put a bracket here, and then the first thing you put is the test or the condition you want to check for. So we want to check if the value of R is equal to 6. There's one thing here, though. Well, first of all, notice that I use double equals because we're checking a condition, right? We're not setting r equal to 6. We're checking whether r is equal to 6. The other thing to note, though, is that remember I said that normally when you use a variable on the left side of the update symbol, right, of the then the rule symbol, then on the left side it represents the new value, and on the right side it represents the old value. However, here we have a slight problem. This L represents the new value of L, but the R we want over here is actually supposed to be the new value of R. So what you do in that case, if you want the new value of R, then you just call it R new with a capital N like that. And then the system will understand that we want the new value of R, not the old value of R. Right? If I had just typed R there, it would have checked whether the previous roll was 6. What we actually want to check is whether the new roll is equal to 6. Okay, now, if that's true, then you tell it what to do in the second input here. In that case, L should be equal to the previous value, L plus 1. Right? And again, here I'm just using L because without, normally using a variable on the right side of the rule symbol means we use the old value. So I want the old value and I want to add 1. Okay. On the other hand, put a comma, and then we'll tell it what value to assign to L if R new is not equal to 6. In that case, we just set it to 0. Right? And now I can close the bracket on the if statement. So again, the format for an if statement is first you tell it the condition you want to check for, then you tell it what value in case that condition was true, and then I tell it what value in case that condition was false. Okay, so that's going to be my new updater. Oh, I think I forgot to enter this, and my new initial state is that. Okay, let's test this. Let's see. Let's try running it 5 times. Let's see. We did roll a 6, right? Actually, on the first roll, we rolled a 6, and that meant that L increased from 0 to 1, right? Because we're working on we now had a 1 6 in a row going, right? But we never rolled any further 6s. So L was reset to 0 and stayed there after that. Let me do it one more time. Roll it. Okay, here we did get 2 6s in a row, right? On the third roll we got a 6, and on the fourth roll we got a 6. So L went up to 2. But then we did not get a 6 on the next roll, so L was reset to 0. Okay. Now here in this case, again, what we want to do is we want to use the run till command to run the system until, in this case, L equals 3. We want the value of L, the L attribute, to be 3, which means that we've gotten 3 6s in a row. So if I do that, gee, that could take a while, right? Ooh, wow, okay. So on this run, holy cow, it took, whoa, let's see. I don't think I'm going to want to do this again. It took 280 rolls before we got 3 6s in a row. Wow, okay. I mean, I think it's working. Let me have one more look at that. Let's see. Did it seem to be working? Like, here's a 6, and L went up to 1, but then we didn't get any other 6s. There's a 6. Yeah, I mean, I think it's working. I think if I were actually, like, doing this for some other reason, I would want to test it. I would want to test it more thoroughly, and probably if you're going to be turning it in, if you're ultimately when you're turning in your project, you're going to want to test this stuff a little more carefully and make sure that it's working right. But for the moment, I'm just going to let it go. I think it seems to be working right. And now let me collect some data. So I'll collect the data for running it until L equals 3, but let me just do it for 1,000 times. I think that should be more than enough. Yeah, okay, let's try that. Okay, this is going to take a while, right? This is obviously, it takes a lot longer to do a single run of the simulation if we're waiting till we get 3 6s in a row. So, let's see, oh, wow. By the way, maybe what I'll do also, I'll do the calculation with using an absorbing Markov chain, so I can get the correct theoretical value for the waiting time in this case, and I can compare it to what we get in the simulation, right? That's useful to know how accurate these simulations tend to be in cases like this. In this case, if I wanted to model it as an absorbing Markov chain, I'd have, how many states would I have? Oh, gee, I'd have probably 9 states, is that right? Because it would depend on what the current roll is, and if the current roll is a 6, we'd want to keep track of how many 6s we'd gotten in a row. And so yes, I think you can model it as a 9-state Markov chain with one absorbing state, the state where you've gotten 3 sixes in a row, and then you could compute the fundamental matrix and calculate the waiting time, right? Okay, so we got our data. Now, what do we want? Well, in this case also we want the mean value of t, right? How long did it take on average to get 3 6s in a row? So, okay, let's see. Ooh, on average it takes 259 rolls to get 3 6s in a row. Okay. And the variance, 64,000. So the mean is about 253. So yeah, so it's quite. The standard deviation is about 254. Yeah, the values are quite spread out, and the mean is rather high, right? You have to roll 259 times, wow, on average, to get 3 6s in a row. But that was not hard to do in Mathematica. It only took a couple of minutes, right, to type everything and to collect the data and to analyze the data to find the mean and the variance, right? So it's actually quite easy to do it. Okay, let's turn to the cats problem. We're collecting letters from the cat food bags until we get a complete set of the letters CATS, right? And we planned that our state attributes would be L, the current letter. We'd have Boolean valued attributes for each of the 4 letters we're trying to collect, C, A, T, and S, and they'll be false if we have not yet collected that letter, and they then become true once we've collected that letter. And then we also have to keep track of the time. Okay, so let's code this up in Mathematica. So state is actually going to have 6 attributes altogether. So we've got the current letter, L. And initially, of course, we haven't chosen any letters. We haven't bought any bags of cat food yet, so we don't have any letters. So L will just be the empty string. And then we've got the 4 Boolean valued attributes, C, A, T, and S. I'll just call them little c. The convention in Mathematica is that all the user-defined variables and constants start with lowercase letters. So I'll make it little c. I'll give it the initial value of false. Remember, this variable represents whether or not we have collected a c yet, and of course initially we haven't collected anything. So all 4 of these variables are going to be initialized to be false. So c is initially false, A is initially false, T is initially false, and S is initially false. Now I've used up the letter T for my for this Boolean variable, so I have to come up with a different name for my time attribute. I think I'll just use the word time, right? Oop, I forgot a comma, but I can just use the word time, right? In computers, there's no problem in using whole words as a variable, right? So time, and of course we initialize that to be 0. Okay, so that's going to be the initial state. And then the updaters we saw, let's see, the updaters were we just pick a random letter, cats, as one of the letters C, A, T, or S with the probabilities 0.3, 0.1, 0.3, 0.1 respectively, right? And then we also have to update the Boolean variables according to whether we've just collected that letter, and we have to update the time. Okay, so updater is a list of rules for updating. Let's see. Why don't I do the easy one first? Time. the new value of time is going to be the old value of time plus 1. Okay, that's easy. The new value of L is going to be a random letter. Okay, now fortunately there is a nice built-in function we can use for that. We can use the random choice function in Mathematica, and the way this works is you give it a list of probabilities, or you can even just give it weights. I'll just give it the probabilities. So we want 0.3, 0.1, 0.3, 0.3. Those are the probabilities for the letters C, A, T, and S. And then I'll say, it's a kind of an odd notation, but then you give an arrow that points to the values that are to be chosen according to those probabilities. So the first probability was 0.3. That's the probability with which we want to choose the letter C. Okay, so that's one of the possible things we can choose, right? We're going to choose a capital C with probability 0.3. We'll choose a capital A with probability 0.1, right? So the second entry here is chosen with probability corresponding to the second entry in the first list. And then we choose a T with probability 0.3 because that's the third entry in the first list. And then finally we also choose an S with the probability 0.3 because that's the fourth entry in the first list. And now we can close that. So that closes the random choice function, right? So there we go. Comma. And now we have to update the Boolean variables, right? So we have C, which is updated. So remember the trick we used. Let me remind you of that. The trick is that we can say that the new value of the C random variable, the C variable, is going to be equal to the old value. In other words, if the old value was true, then the new value will be true, or it'll also be true if the current letter is a C, right? So in other words, if the old value is true, that means we had already collected the letter, and so the value of this attribute C should continue to be true. On the other hand, even if the old value was false, we're going to make it true if the current letter is a C. So we can do that easily in Mathematica. We'll say it's the old value of C, or, now shorthand in Mathematica for or is 2 vertical lines, right? That means or, shorthand. So either C was true already, or the current value of L, and here I want to use L new, because I don't want to look at the old value of L from the previous bag of cat food. I want to look at the new value from the new bag of cat food, and I want to say if that new value is equal to a C, then we want to update the value of little c to be true. Right? So the new value of little c is equal to the old value of little c, or if the new letter is equal to a capital C. And then we repeat that for each one of the 4 Boolean variables. So A goes to A, or L new equals A. Notice again I'm using the double equal sign here because we're testing for equality. Right? So this expression L new equals A, that returns either true or false depending on whether the new value of L is in fact equal to A or not. And then we'll do the same thing for T and S. So T updates T or L new equals T, and S updates according to S, or L new equals S. Okay, and oh, actually that's it, right? So now I've got all 6 updaters for the 6 attributes. Okay, so that's my my list of updaters. And now I can test it out. Let's see if it's working correctly. So I'll try running it once, right? So I'll give it the initial state to run on. I'll give it the updater, and I'll just ask it to perform the update operation once. So we'll see what happens when we buy 1 bag of cat food. Okay, let's see, what did happen? Well, Well, initially, of course, the first line here, this is the initial state before we bought any bags of cat food. Then we bought 1 bag of cat food, time advanced to 1. The letter we got in the new bag of cat food was the letter T, and that means that all the Boolean variables were still false except for the T, because now that we've collected the letter T, little t becomes true, and it should remain true forever after this, right? Because we've collected the letter T, we don't have to collect it again. Let's see, let's test it a little more. Let's maybe run it for, let's buy 5 bags of cat food and see what happens. Okay, so the first bag we got a C, the second bag we got a T, the third bag we got an S, the fourth bag we got an A, and then we got a C again. In fact, we actually did end up collecting all 4 letters, right? And you see, it actually only took 4 bags of cat food until we collected all 4 letters. And that's as fast as you can do it, right? Because you do have to collect 4 different letters. You can't do it any faster than by your 4th bag of cat food. Okay, so that looks good. Looks like it's working. Now let's try the run till command, because what we're actually going to want to do is we're going to want to run this system until we've collected all 4 letters, right? So we'll run it on the initial state with our updater, and we'll run it until all 4 of these Boolean conditions are true. So A is true, C is true, T is true, and S is true, right? So we run it until A is true and double ampersand, that's the Mathematica shorthand for logical and. So this says A is true and B is true and C is, sorry, not B is true. Let me try that again. Well, I'm not going through the alphabet. It's C is true and A is true and T is true and S is true. Right, those are the 4 things we're keeping track of, right? Okay, let's try that. Okay, so this time apparently it took 8 bags of cat food until we were able to collect all the letters, right? So the first bag we got an A, second bag we got a T, and then another T, and then another T, and then another A, and then a C, and an A, and finally the last letter we collected was an S. That gave us a complete set. That took 8 bags of cat food. Okay, that's plausible. That can happen. I can run the very same line again. I'll get a different result because I'm using the random choice function, so everything is randomized. Let's see, this time it took 15 bags of cat food, right? We got a T, 3 C's in a row, an A, a T, 3 C's in a row. Oh, and this time we had to wait a long time to get the S again. Huh, that's odd, because S isn't the rare letter. A is the rare letter, right? But okay, this can happen. You just had bad luck. You weren't able to collect one of the common letters. Okay, this seems to be working correctly. So now we can try gathering a lot of data. So I'll set our data equal to, oh actually, let me do this. I'll copy the previous one, but I'm going to change the function from run till to run till many, right? So basically I'm going to do exactly what I did in the previous command, except now I'm going to run it 1,000 times, right? So I'm going to run the system 1,000 times and collect all the data from 1,000 runs, right? We're simulating repeatedly buying bags of cat food until we collect all 4 letters, and we do the simulation 1,000 times. Semicolon so it doesn't print 1,000 data points for me. That would be too ugly. So run this. Ooh, I accidentally hit a period. Okay, let me try that again. Ah, there we go. Okay, it's going to take a few seconds to do this. We're halfway there. Okay, we got our data. Now, what we're really interested in, in fact, I think what the question said was, on average, how many bags of cat food do you need to collect until you get a complete set of letters? Okay, so that means what we want is we want the average of the t value, right, at the last state in the run, right? Okay, so we can use our mean of command, mean of data, and we want the average in the data of the t attribute. I'm sorry, not the t attribute, the time attribute. The t attribute is whether or not the t was collected. Of course, that will always be true at the final state in one of these runs, but the time attribute will vary from run to run. Okay, let's try this. Oh, okay, so it takes about 12 bags of cat food on average until you get a complete set. Again, you know, if you want, you can try taking the variance, see what the variance is, how much variability there is in collecting bags of cat food. Variance of data, time, so that, and the square root of that is what, like between 8 and 9, so yeah, so there's a reasonable amount of variability. Right, the standard deviation would be the square root of the variance, that's between 8 and 9. Okay, one other thing, you know, there are other questions you can ask about this. One thing you might ask is, what's the last letter, what's the last letter collected? Now remember, I pointed out it seemed odd in the case of this run that the last letter collected was an S, that it took actually 15 bags of cat food till we got the S. That seemed a little bit odd because S is not a rare letter, right? A is the rare letter. So you might think most of the time the hardest letter to collect is going to be the A, and therefore most of the time you'd think that the A is going to be the last letter collected. So that will actually be reflected in what the L attribute is, or the value of the L attribute in all of these data points, right? The L attribute in all these data points, that'll record what the last letter collected was, right? Because that's the last state of the system during the run. So there's another convenience function that you can use. It's called count val. Count val. So I want to count the value of the L attribute. I should say I want to count the number of times the L attribute took a certain value, namely A, right? Because that's the rare one. So let's see. In the data, I want to count the value of L, and I want to count the number of times it was equal to capital A. Right? So this should return a number between 0 and 1,000. Right? It's going to return the number of runs, number of times during those 1,000 runs that the letter A was, in fact, the last one collected. 601 times. Okay, so that seems right. More than half the time, the last letter collected is going to be the A. Right? And you can, you know, check it with the other letters. So, for example, C happens much less often that C is the last letter collected, and try it with T, it's probably about the same, yeah, and S. They're all in the 130, 140 range, right? So, except for A, because that's the rarest letter, so that is usually, 60% of the time, it's the last letter collected. Another thing you might be interested in is you might want to get a visual feel for the range of numbers of bags of cat food you have to buy. So there's also a histogram function you can use, histogram. And the way it works is you give it the data, you give it the quantity that you want the histogram on, right? In other words, we want to know, oh, by the way, remember, histogram is just a kind of a bar graph of the frequency of each value in a particular data set. So I'm going to get a bar graph of the frequency of each of the times in the data, right? So I want the histogram of the time in the data of the time attribute, and you also have to give it a range of values and a width for the bars of the histogram. So in other words, let's see. I don't know, I'll just go from 0 to, I don't know, to 100. I doubt that it would ever take 100 bags of cat food until you collected just 4 letters. I guess it could happen. So I'll go from 0 to 100, and I'll do it in increments of 5. So this will return a histogram where each bar of the histogram represents the time values in groups of 5. So the first one will be 0, 1, 2, 3, 4, and then the second one will be 5, 6, 7, 8, 9, and so on. Okay, so it gives you both the table of values, but it also gives you the histogram graph, right? So the first bar here, it says evidently there were 55 data points where it took between 0 and 4 bags of cat food, right? This is a 5. This is a bar with 5, right? It goes from 0 to 5 on the x-axis, and x-axis represents the time, right? The number of bags of cat food. So 55 data points where it took 5 bags of cat food, 459 data points where it took either 5, 6, 7, 8, or 9 bags of cat food, and then from 10 to 14 it was 234, and so on, right? By the way, the only way the time could be from 0 to 4 is if it were exactly 4, right? Because you can't possibly collect the 4 letters with fewer than 4 bags of cat food. So in fact, this is telling us that there were exactly 55 data points where the time was exactly 4, right? And you would expect that to be unusual, right? That's not going to happen very often, that the first 4 bags you buy are going to contain 4 different letters, and you're going to be done, right? You win the prize after 4 bags of cat food. Okay. Okay, now let's do the last example from the previous lecture, how to do a computer simulation of a standard Markov chain, right? So I'm gonna do a simulation of a Markov chain that has 9 different states, and remember we agreed in our plan that we would simulate it with simulation states that have 3 attributes. S, which represents the state number of the Markov chain, T, the time, in other words, the number of time steps that have occurred, and this vector C, C for count, it's the vector of counts of how many times each state has occurred so far in the run of the system. Okay, and then we update it by, we pick a new state, S new, that's going to be chosen according to the probabilities in the row of P that corresponds to the previous state, right? That's how Markov chains work. Tn is T0 plus 1, and Cn, the updated count vector, is going to be exactly the same as the previous count vector, except we add a 1 to the component corresponding to the new state that we're in, right? So we update the count in that one, increment that count by 1. Okay, here's the vector I'm going to use, the P matrix. It just, the transition matrix I'm going to use. It represents a 9-state transition matrix, so it's a 9 by 9 matrix. All the rows add up to 1, right? A probability matrix. So I just generated numbers at random. It's clearly a regular Markov chain because there aren't even any zeros in this matrix. So you can get immediately from any state to any other state, and the period is clearly 1, and so on. Okay, so according to our theory, this will have a nice, well-defined W vector. But let's see if we can determine the W vector using the computer simulation. That should give us approximately the same answer we would get theoretically by computing the W vector. Now, before I start typing in the state and the updater, I want to first define a useful kind of auxiliary function, utility function that'll come in handy when we're working on this problem. I'd like to have a simple way to produce a vector that's all zeros, so a list of numbers that's all zeros, except it has a 1 in a particular position, right? Since this is a Markov chain with 9 states, I'm actually going to want to be able to easily produce a vector that has 9 zeros in it, except it has a 1 in some particular position, right? So what I'll call this the 1 function. Does that work for you? The 1 function. And remember, one of the quirks in Mathematica is when you're defining a function, you the variable in the list of arguments and the list of inputs when you're defining the function, the variable has to be followed by an underscore, and that tells Mathematica that this is a variable that matches anything you give it. So it's a kind of a peculiar syntax quirk, but that's the way it is. Okay, so the input's going to be the variable I, and then what I want to do is I want to, well, basically I'm going to start off with a vector that's all zeros, or a list that's all zeros. Well, there's a nice built-in function that produces an array in which all the entries are the same element. In this case, I want an array that has 9 zeros in it. So the way the constant array function works is first you tell it what element you want to repeat. I want to repeat the element 0, and then you tell it how many times you want to repeat it. I want to repeat it 9 times. Okay, so that just gives me a vector of all zeros. Now that's not quite what I want. I want to start with all zeros, but then I want to replace one of those zeros by a 1. So there's another built-in function in Mathematica, the replace part function. And so what I'm going to do is I'm going to apply the replace part function to this constant vector of all zeros. And the way the replace part function works is first, the first input is what array or list or vector you want to start with, and the next input is how you want to change it, and that is where you want to change it and what you want to change it to. So I want to replace the ith part by the number 1. So this is the syntax. This is the convention that's used in Mathematica. The first thing here, the I, tells it which part to replace. I'm going to replace part I of this constant array. The arrow tells you we're going to replace it with something, and the 1 tells you we're going to replace it with 1. So this says start off with a constant array of all zeros, 9 zeros in a row, and then replace the ith part by a 1. Okay, so that's the definition of the function. Oh, by the way, also note that when you define a function, you use colon equals, because colon tells it that this has to be reevaluated every time you use the function, right? Every time I use the one function, it has to reevaluate this expression, right? It doesn't just set the value once and then just reuse the same value and over and over again. Let's test it out. I don't trust anything until I've tested it. 1, 2, what should that give me? Well, that should give me a list of 9 numbers where all of them are zeros except the second one, right? So all the entries should be zeros except the second entry should be a 1. Ah, good, okay. So what about 1, 7? Well, that should give me a list where all the entries are 0 except the 7th entry is a 1. So that worked. Okay, so that looks good. Okay, now I think I'm ready to go to work. This one function will come in handy when we're doing the state and the updater. So, state. First of all, well, okay, how about the time? No, why don't I start off with a state? So S, right? That's going to represent which state we're in. S is going to be some number 1 through 9. Now I have to start the Markov chain off in one of the 9 states, right? I can't really start it off in no state because then I wouldn't know what probabilities to use to determine the next state, right? Remember, in a Markov chain, you have to know what state you're in currently in order to know what probabilities determine the next state. So we have to start off in one of the 9 states. So I'll just pick one at random, maybe 5. Okay, I'll start off in state 5. Turns out it doesn't really matter in this case what state you start off in, because being an ergodic Markov chain, once you start off in any state, you very quickly find yourself in all the other states. So it doesn't really matter what state you start in. You're going to get the same long-range behavior regardless. So okay, but we can test that later by changing the starting state. But for the moment, let's just say we start in state 5. Let's see, the time initially, I think we should start the time at 1 this time instead of 0, because we are starting the system in a particular state, and so this is going to be one of the states that's counted in the time. And then the initial C vector, remember the count vector, the list of all the counts, all the times the system has been in each of the 9 states, well, that will be given by this one function. We can use 1 of 5, right? Because at this point we're starting off in state 5. That means we've spent one time step in state 5, but we've been in all the other 8 states 0 times, right? So this is exactly the correct count vector for starting off this system, right? We want all zeros except we want a 1 in the 5 position. Okay, so that's the initial state that we'll use, right? And notice that The one function worked correctly. It gave us a list of all zeros except with a 1 in the 5th position, and that means that we've been in all the states 0 times except for state 5, which we've been in once, right? That's what that means. Okay, now we do the updater. So the updater is going to be a list of update rules. So let's do the easy one first. Time is easy. Time gets updated to be the old time plus 1, as usual. What about, let's see, what about the state? S, how does that get updated? Well, that gets updated according to the probabilities in the row of the P matrix that corresponds to the current state. So if we're currently in state 5, for example, then we look at the 5th row of the P matrix, and that tells us the probabilities to use in determining what the next state will be, right? That's how Markov chains work. So what I want to do is choose one of the numbers 1 through 9 according to the probabilities in the row of the Markov chain corresponding to the previous state. Well, okay. We can use the same built-in function that we used in the last example. We can use the random choice function, because remember the way this works is you give it a list of probabilities, and then you give it a list of values, and then it'll choose one of the values according to the probabilities that you gave it, right? So the probabilities we want to give it are the row of the P matrix corresponding to the current state that we're in. So that's going to be the P matrix. Now we can select any row of the P matrix by using double brackets. So double bracket S, double bracket, that picks out the row S of the P matrix, right? Because each row in the P matrix is represented by a list, and row S is going to be the sth row of the P matrix, right? So or the sth item in the list of the P matrix. So those probabilities in the row S of the P matrix, those give us the probabilities for choosing the next state. The next state is actually going to be one of the numbers 1 through 9. I could just type a list of the numbers 1 through 9, but I'm lazy, so I'm going to use the range function, which is just a convenient way of listing a list of numbers, right, in increasing order. So I'm going to do the range from 1 to 9, and that'll just list the numbers from 1 to 9. Okay, and next. Oh, I'm sorry, I forgot to close the bracket on the random choice function. Okay, so random choice, remember the weird way this works. First you give it the list of probabilities, then you type an arrow, and then you give it the range of values it's supposed to take according to the probabilities that you gave it. Okay, so that will choose a new state. Then also we want to update the count vector. So the count vector, as we said, it's going to be the old count vector plus we want to add 1 to the position corresponding to the new state. Well, this is another place where this one function that we defined earlier comes in handy. I can add to the C vector, I can add the 1 vector that we get by replacing a 1 in the position corresponding to the new state. So I have to type S new, right? Because normally on this side of the rule, on the right side of the rule, S would stand for the old S value, but here we want the new S value. We want to update the counts according to what the new state is. Okay, so, and then as I said, the 1 function, this will give us a vector of all zeros except with a 1 in the S new position, and when I add it to the old state vector, it'll add up all the corresponding entries, and the only entry that'll change will be the 1 in the S new position, which will get incremented by 1. Okay, so there's my updater. Now, I think we're ready to test it. Let's see. Let's try running it. So we'll apply it to the starting state. We'll use the rules from the updater. And let's just run it once, see what happens. Ah, good, okay. So what happened was, the second the second state that it reached at time 2 was state 7, right? So it started off in state 5, and then it moved to state 7 at time 2. And the new count vector has been updated, and it shows that we've been in state 5 once, right? Because the 5th entry in the count vector is 1, so we've been in state 5 once. And also the 7th entry in the count vector is 1, because we've been in state 7 once. All the other entries are 0, because we haven't been in any of the other states at all. Okay, let's test it a little more. Let's try running it 5 times, right? So now it started off in state 5, then it moved to state 2, then it went back to state 2 again. That's possible. Then it went to state 3, then it went to state 5, then it went back to state 3. And here's the final count vector. Let's see if this looks right. It says that we were in state 2 twice. Is that correct? Yes, we were in state 2 twice, right, over the history of this thing. We were also in state 3 twice. Yeah, that's also true. We were in state 3 twice. We were also in state 5 twice. Yes, we were in state 5 at time 5 and also at time 1, right? And we weren't in any of the other states, right? All the other states have count 0. Okay, that looks right. Okay. So that seems to be working properly, right? Then what we want to do is we basically just want to start the Markov chain running, and we want to run it for a long time. I don't know, maybe like 1,000 times or something, right? So let's use the run many. I think this is a new one. I don't think I've used this one. Run many without the till in it. Run many. Basically I'm just going to, let me just copy from above. Let's see. Yeah, let me copy this from above, but I'm going to change run to run many. Now, first two inputs are the same, the starting state and the updater. The third entry is going to be how many times I want to run it on each run. In other words, how long do I want to let the system run on each one of the trials I'm going to do. Well, let's say we'll run it 1,000 times on each trial, right? So every time we do a run, we'll run the state for 1,000 time cycles. But then how many times do we want to do that? How many trials do we want to do for running the system long term? Let's not do too many. How about just 100? Because this turns out to be a little bit on the slow side. So let's see what happens. Oh, so what this is going to produce is it's going to produce 100 data points. Right? That's the number of runs. Each data point is going to represent having run the Markov chain for 1,000 steps. And that means it's going to show you the final state after running the Markov chain for 1,000 steps. So each one of the data points here is going to have time equal to 1,000, and then it's going to have a count vector which represents a count consisting of all the times it was in each of the 9 states. So this is going to be my data. Let's say data equals that. Again, I don't really need to see it all, so I'll put a semicolon at the end. Let's see. Yeah, this is kind of slow, right? It's 6, 7. We got to get up to 100. This is kind of slow because each time it does a run, it's actually running the Markov chain for 1,000 time steps. So yeah, it's a little time consuming. Let's see. One thing we would like to do when we've got our experimental results is we would like to compare this with the theoretical results. Remember that in the long term, the amount of time it spends in each possible state will correspond to will be given, in fact, by the stable vector W, vector of stable probabilities, and we can calculate that using Mathematica by finding the eigenvector whose eigenvalue is 1 of P transpose, right? That corresponds to the stable vector. And so we can do that also and see what happens. Okay, there we go, we're done. We got our data. Now what we want is we want the average of the C values. Let's see. So I can use the mean of function again. Even though C is not a number, it's a vector, I can still take its mean. I can take the mean of a vector because you just add up all the values and divide by 100, right? So the mean function will still work here. So I want the mean in the data of the value of C, right? Okay, there we go. So on average, it spends 114 times in state 1, 133 times in state 2, and so on, right? So it seems like, oh, and it spends relatively little time. What is this, state 5? Yeah, it doesn't spend too much time in state 5, only 71 out of 1,000 time cycles. If I want to convert these into probabilities, I just divide by 1,000, right? Because there was a total of 1,000 runs. So these numbers should add up to 1,000. So if I want the probability of being in each one of those states, I can just divide by 1,000. Okay, so those are the probabilities. Now, this should be a good estimate for the W vector, the vector of stable probabilities. To test that, why don't we actually compute that? What we want to do is you want to do the eigensystem of the transpose of P, the P matrix. Okay? Let's take a look. Let's see what we get. Ooh, that didn't take long. Okay, so the first eigenvalue is in fact 1, and that means that's going to correspond to the first eigenvector they give us. Right? So that's the first vector in the list of eigenvectors. So there's that. Let me copy and paste that. So it seems that our W vector, well, it's kind of determined by this, right? Notice all the imaginary parts are 0, so these are really real numbers. And in fact, they all seem to be negative real numbers. But we do want to normalize the W vector so we get probabilities. Okay, so I'll use the trick I showed you. We'll take W vec is equal to W vec divided by, what do we get when we add up all the entries in the W vector? So plus at W vec. Oh my God! Oh, I forgot. I have to capitalize plus because it's a built-in Mathematica command. There we go. That's better. So yeah. So it, theoretically, it's supposed to spend the probability of being in state 1 is 0.1167. What did we come up with back here? In fact, let me just copy this. We came up with 1148. That's pretty good. It's accurate to about 2 decimal places, right? Let's compare them here. And then the second entry, theoretically, it's supposed to be 0.133. Yeah, that's what we got, right? So that was accurate to 3 decimal places, and the third one is supposed to be 0.111. Well, that was that was pretty good, accurate to almost 3 decimal places. So it seems that our simulation worked. We got an estimate for the W vector that's pretty close. It seems to be accurate to at least 2 decimal places.